Let me start my first lecture. Actually, I will give you two lectures this week and next week. And my topic in this course of the lectures is signal processing. Because this is a very big challenge because I don't know your backgrounds, which school did you graduate, and which field are you now measuring? So I try to start a very, very fundamental idea about the signal and its processing. So, any of you feel that any point is not clear to you, please ask me. I think I can pick your question during my lecture. Otherwise, I can answer you after the lecture. And also, you will have to pursue the exercise and practice after this. That's gonna make your understanding deeper, I hope. So this is the only lecture. Only lecture cannot complete your knowledge and skills. So I hope you can use the knowledge here for the solving your real problems through the practice and also through your research. Okay. So actually I am trying to talk two things in 2 weeks. Oops. Which is not. Okay. Let me use hand microphone. And the first topic actually is denoising. All data you will collect from the real world has more or less data error or data noise. So first thing we need to do to face on real world data is reducing the noise from the data. This is the first lecture's main point. And I'm going to talk about two different classes of noise. First noise is deterministic noise, and the second noise is a stochastic noise. Okay, but before talking about that, let me briefly define what we're going to do through this lecture. Okay. First of all, we need to know what is signal. What is the difference between data and signal, and what is noise as well? And we're going to thinking about the denoising method for these two types of noise. So what is signal? This is one typical example of data that you're gonna be dealing with. Here's a population of each ward of Nagoya City. Chikusaku and Minatoku, Nakagawaku. Those wards have a big population. But Atsutaku and maybe Nakaku, they don't have a big population like this. So you can see these numbers as meaningful numbers in terms of the population. And also you can figure out the mutual comparison, relative value of these values by plotting the bar that is proportional, that has the proportional height of these numbers. So these numbers are clearly data that you need to do with something. Okay, so these are data. So what is a signal? By that mean, signal is like this to me. Let's see, that was the population, but this is also the population, total population of Nagoya City, which is plotted against to the time line, like the April of 1908 And this is the 1 year population change, and the April of 1099 and April of 2000. So this figure represent also the numbers, but those numbers are ordered. Ordered according to the timeline. So the data is somehow, signal is the data, but that signal is also associated with the kind of order, like a timeline or spatial location. Those has an order, okay? Higher, lower position. And yesterday, today, tomorrow. So ordered data are usually called signal. And that is the target of the method of signal processing. Okay. So by watching this graph, we can learn that the population of Nagoya City is growing, but its speed is somehow reducing after 2009. And we can also see the dip of the population at the April. Probably people move in April. You go away from Nagoya City, and someone will come to Nagoya City. But between that time period, you may have a dip, like 1,000 of population. So you can understand these things from this figure, which means that these are, how do I say, these numbers, data, doesn't mean such thing, because these numbers are not ordered. Even you plot the figure according to the number, you don't also see, or you don't see that any tendency or trend or something like that. So that's a big difference. This and this. This is signal, and this is statistics. Okay. So please be clear about the difference between data and signal. And signal can be characterized by the implicit order of the data. Okay. So this is a very simple but very important characterization of data. Signal. And I talked about 3 very important characteristics of the figure, right? First one is the total population of Nagoya City can be seen from this figure. Although it is increasing, but in the average, you can say that the population of Nagoya City is 2 million or 2.2 million, like that. This is here or here. Okay, this is the average of the population. And also the growing is somehow steady and is somehow reducing. This is a global trend of change. And finally, we can see the small but periodic change of the population. The period of change is 1 year. So those 3 things are very important in thinking about the change of the Nagoya City's population. Therefore, those 3 numbers or those 3 ideas should be correctly characterized or calculated from this signal. That is a very, very fundamental function of signal processing. So how can we do that? It is very simple, actually. By the way, it is very simple. By the way, this is the average, and this is the trend, and this is the periodicity or periodical fluctuation. Okay, we see 3 different things on this figure. One is the average, one is the trend, and the other one is fluctuation. Okay, so to understand these things, not seeing that figure, but calculating the signal or processing the signal by the computer system, That is digital signal processing area. So again, let me clearly define what is a signal. In this lecture, we define signal as an ordered sequence of data, which mathematically are represented by this. This is a variable and ordered by the index. An index is usually positive regular value, positive integer value, but also it can be a negative. And if you think about the spatial order, you need 2 or 3 indices like x, y, z. So if you like, for example, think about the distribution of temperature in this area or in this room, that's going to be clearly represented by 3 indexes like x, which is indexed by I, j, k, if they are represented by a discrete position, and I, j, k are all positive integer. This. In this case, you can think about 3D grid points in a arbitrary space. I'm sorry, I'm very bad at writing or drawing, but things like this, I hope you can understand. So as a 3D grid can be, indices can be represented by 3 indices like this. So, because I'm in the speech field, we usually deal with the one-dimensional time sequence, which is the speech, because speech is the sound pressure, but it's varying very fast. But if you are thinking about, say, image signal processing, then probably your main target is the 2D, 2D image, X and Y, or horizontal and vertical. Those orders are very important to you. So if it is ordered, then data can be, can be characterized by, for example, proximity of the index, which is a local, local characteristics. Like, for instance, in this case, the April 1099 is very close to April 2000. That is closer than April 2009. Okay, so these two data should be somehow should have somehow similarity, or more similar than this and this, and comparing to this. So this is the proximity of the index, and it should be reflected to the data value itself. So signal processing is understanding signal such a ordered number, ordered data. Okay, so I plotted 3 lines here on this figure. Again, let's see the local change of the Nagoya city population against the year. Okay, and as I suggested, there are 3 very important characteristics of the signal. One is average value, and the other one is a global trend, and the third one is periodical change. Okay, so how can you calculate, for instance, average out from this signal? How do you calculate? So total number. Yeah. Okay. So total can be calculated by I is equal to 0 to t. Let's see. Here's a t period. And xi. This gives you the total number, n. This is the total numbers. And average usually can be estimated by, oops, sorry. This is very sensitive. I'm very bad at that. Divided by total number. Okay. Yeah. In this case, t plus 1. No, because it starts from 0 to t, therefore you need to divide t plus 1. This is the average. And how do you understand trend? Because thinking about the way of calculating this value is how do you understand trend is. Okay? So how can you calculate the trend? I mean, this line. Do you have any idea? No? Okay. So actually, I plotted this line so that this line goes almost in the middle of these fluctuations, which means that I averaged the also samples, but in a very short term average, like 1 year. Okay? Because if you average the samples over 1 year, then naturally these dips should be cancelled, right? Do you understand my point? Therefore, local averaging can give you a trend, which is given by this. Of course, trend also a signal because it's change against to the time change. So let's see, a trend can be written like y m. The yn is equal to say 12. 12 is the number of the month, and I minus 5 to I plus n. N minus 5 to n plus 6 xn I is equal to xi, something like this. Do you see my point? We also calculate the sum and divide it into the number of the samples, but it range of the averaging is shifting one by one, right? But the width of the averaging 1 year did not change. By doing that, we can cancel the fluctuation during 1 year. Okay? Do you get my point? Okay, so this is kind of a local averaging or smoothing. Okay? If you do the smoothing, then. So here's the engineering. How do we choose the number or period of the averaging? It's very big important and very big problem, a big issue. And because we know that this time axis represents a month, therefore we know that 12 is very meaningful number for the months because that represents 1 year. So we need this knowledge in order to calculate the meaningful numbers. Otherwise, if you do, for instance, 3 or 5 local range, you still have this kind of dip again. Okay. And the final thing, periodicity or periodical, fluctuation. This is very difficult, but if you specialize in signal processing or engineering, you will later, or you have already studied about the Fourier analysis or spectrum analysis. If you know about that, or if you are familiar with that, you may know how to pick these periodicity. But obviously, this is 1 year because this is a social statistics. Therefore, socially meaningful things, a 1 year period But anyway, the easiest way to extract this information from this signal is, to me, like this. Because we know x. Okay, suppose that this is the average of C. We can subtract average and also trend, or maybe we don't need to. Okay, x minus trend should be equal to periodical fluctuation Pn. Because after subtracting this part, we'll be able to see only a change of the signal. So this is a very fundamental calculation of the signal. But we still say that this is a, but I like to say this is a fundamental signal processing. So let me, determine some wording, okay? So if x, okay, data or signal is somehow has the nature of the probabilistic behavior, we can say that x is a stochastic variable. Stochastic variable. This is very important what you need to know, stochastic variable. And if the stochastic variable is used for somehow calculation of a number or numbers, these number or numbers are called statistics. So average is a statistics of the population change of the Nagoya city, for instance. So this is called statistics, okay? You usually suppose that statistics is the average or variance or a skewness or things like that. But, generally we call the values that is derived from the stochastic variable is statistics, okay? So Yn, this is also statistics of the x, because we have derived these sequences or numbers are from this. And of course, Pn is as well. So statistics are calculated from the stochastic variables, okay? So, actually I defined that, T, trend, as a, value which is after subtraction, calculated after subtraction, therefore. So this is, more beautiful writing of the previous equations, but has three methods. And let's see what can we get by doing this calculation. And, certainly, of course, the average is a single value. It doesn't depend on the time sequence. So, of course, it is constant, and it is like 22,000 and 2.2 million, just like average of Nagoya citizens. And trend can be calculated like this, which means that over the years of the statistics, we have only 1,000. Like 1,000 of people are, changed during the period. So it is very steady, and the residual component or the rest of the data can be depicted like this here. This is the periodical element or fluctuational element of that data. Okay, so if you know that the correct correspondence between indexes or proximity and data distribution or data itself, we can calculate these things through a very, very simple mathematics. And it gives us a very important hint to predict future or to understand what is going on. That is a very basic also aspect of the machine learning or big data analysis. Okay, so this is a introduction of the signal processing. And this. Okay. あれこれなんでないんだろう Okay, and I'd like to give you one very important thing, which is model. Because we have theories of probably social theory of the population, for instance. I have not deeply studied about that, but such scientists may have a model that can describe the change of the population against the time. And if it is useful, it is written in also a mathematical form. For instance, one scholar thinks that the population against time can be described by average value and linearly increasing value. A is constant and n is the time. So this means that every 1 month you get a certain increase of the population. And also fluctuational part. And I will tell you later, but I think we can rewrite the periodical component through a sinusoidal function like this. Probably omega 0 n plus phi. Okay. So, of course, this simple equation, which has 3 parameters, average and global trend in linear manner, and also periodicity and periodical amplitude, and maybe phase. So we have 1, 2, 3, 4, 5 values or parameters, and cannot, exactly represent the real x value, which can be only observed. We need add in general error term, En, and this is the error term. So supposing that say for instance, the medium size or large size city in Japan and can be, or its behavior of the population can be represented by this model. Is the, how do I say, mathematical approach of the social science. So social scientists have some idea, and they represent the idea by means of a mathematical representation, which says that the increasement of the city volume is proportional to the time. So that is, of course, a very wrong and too simple hypothesis, of course. But hypothesizing something should be somehow related to mathematical representation. Other than that, we can, develop, or we cannot use the signal processing theory for the further confirming the theories or predicting the future based on that view. So most of the data science or data mining problems can be regarded as estimation problem of these model parameters. Here in this case, C, A, B, omega 0, and phi. Okay? If you can determine these values from the observation, then you can foresee what will happen, right? Or you can express the change of the different city in the different data set. So that is universal problem, because thinking about the model is your job, and confirming the correctness or even estimating these values are kind of common sense these days. And you can use MATLAB. You're gonna practice how to use MATLAB. Well, also ours. A lot of good tools can give you a good estimation of these values. But building this equation is the only one thing that only you can do. Computer cannot hypothesize these kind of things. Of course, you can use a simple polynomial, function or things like that, but that doesn't represent the basic idea. The important thing is to bring a sinusoidal function in order to represent the periodical change of the population. And in fact, it is much better to use squared cosine, because cosine is like this, but squared cosine is like this. So, which is look like more similar to this black line. So, please be fluent to, think about your idea on the mathematical domain. You do not use very complicated math like, differential or integral or blah, blah, blah. You only have to know that simple math like a multiplication or subtraction or maybe kind of a periodic function. That will, gives you a very accurate representation of your idea on the mathematical domain. And based on this mathematical domain, you can easily estimate these numbers. So estimating these numbers will be discussed the lecture in next week. But this is signal processing and this is signal representation. Okay. And so actually I used the sinusoidal signal without explanation, but I'm afraid that some of you are not so much familiar with the mathematical representation of the sinusoidal signal, in particular discrete domain. But this term or this equation completely describe what is a sinusoidal signal is. So if you change the omega 0, then the basic periodicity will be changed, and if you change the phi, then the signal will be shifted forward or backward. And if you change the amplitude A, then the height of the signal will be also controlled. So if you see a sort of periodical phenomena, you may use this very simple representation. So we have a lot of periodic values when you observe something. Day, for instance, day in temperature of the day. Clearly, we have the period of 24 hours. Or if you measure the day of time of the daybreak, it is also have a periodicity of 365. Finding those, periodic value was a very crucial problem of the people in ancient world. And, so to understand this kind of mathematics to represent your idea onto the math, is very useful and important. So if I have time, I like to talk more. I can talk, 2 hours using this figure from my expertise, but I cannot. I don't have such time. So let's move to the next stage. Okay. Again, here's a formatted version of the previous equation. The population at the time index n can be calculated by average, trend, and periodical information with a small amount of error. And if your model is very accurate, then this value should be completely random variable. Random variable, that is random. But if you have a very wrong and worse model, then this value, error value, should have some sort of still characteristics against 2n or very, biased error or things like that. So model parameters and, estimating those parameters is a fundamental problem. Oh, by the way, you don't have this in your handout? Oh, I'm sorry. Okay, so let's move on to the noise reduction. So any students who do experiment or any student who deal with the real world data should be annoyed by noise. We cannot estimate the real value of fluctuation or any phenomena which have some sort of a randomness. So noise reduction is a very important pre-process for data analysis. So I'd like to discuss about that point. One of the most difficult point of noise reduction is we don't know what is noise. Okay? We even don't know what is signal. Its inherent meaning. Because, for instance, in the previous examples, we had at least this time sequence of the data has 3 different meanings. One is trend, one is average, one is periodical fluctuation. All those 3 components are all important. But if you like to, for instance, focus on the trend, then fluctuation and noise. You don't need that information. But if you like to know the period or periodical information of this data, trend and average are noise. Okay? So it depends. What do you like to know? That is the one very difficult part of noise reduction. Okay, so like I say, defining noise is not always simple. It depends on what you like to know from a signal. Either of the average, trend, or periodical fluctuation may be a noise. It depends what you like to say or what you like to do. So you need to know about what you like to know and what you don't like to know. And because noise is a very, very, very fundamental, so there are a lot of different noises. But simplest noise is the additive noise, which can be mathematically represented by this equation. Suppose that S is the real signal. I don't know again what is the real, but suppose that Sn is a real signal, and N is a noise. And noise and real signal are added. And that is the observation that you have, or measurement, or maybe survey result for social scientists. Okay? So this is called additive noise. Against to that, on the other hand, we have productive or multiplicative noises. That is much more headache to the engineers. But we simply suppose that the noise is additive. And if you agree with this representation or model, estimating the real signal is quite easy because you can rewrite this equation like this. Sn can be calculated from xn minus t. As far as you know what is dn, then you can calculate, of course, real value. But unfortunately, we never know what is noise. It is more difficult in some cases to know the real signal. So the noise reduction actually is a big headache for the data analytic people. Okay. So again, we don't know what is the actual noise signal here. So let's start a very simple example, which is known as power supply noise. This is a very special noise for the electrical engineers, right? If you plug in to the power outlet any sort of measurement machine there, then because electric power is transmitted based on the 60 Hertz alternative current or voltage of electricity. Therefore, it sometimes leaks to the very sensitive measurement systems. In this case, these small, peaks represent what you are measuring now. But, that is contaminated by these periodical power noise because of the leakage of the power onto the signal measuring system. I think, if you are studied in engineering school, you may have had this sort of signal. I studied in electrical engineering, and we have a lot of this headache for the lab because of the leakage. And chatting this leakage is not easy for physically. But if you are very good at signal processing, then actually you can do that after measurement in some lucky cases. Okay, so how do we do that? That is the second part of this talk. But anyway, this signal is somehow known by us. We know that this is a 60 Hertz power signal, which means that we have some knowledge on the noise. That is a very lucky case because in general we don't know what is noise is. Okay, so what we know is that this is 60 Hertz signal. In other words, this signal can be represented by A cosine and 12 over 2 pi n plus some phase, which means that I can model the noise by a very simple math. Okay. So this is the periodicity of the signal. Okay. So again, 60 hertz is the periodic. The periodicity is like. So what was this slide for? I forgot about that. The period. Yes. The period is. Do you understand hertz? Hertz mean that it alternates 60 times in a second. Okay. So in other words, we have 16 fundamental waveform in a second. So the period is 60, 1/60 second. So the wavelength at 1,000 hertz. By the way, I'm assuming that these signals are sampled at 1,000 sampling frequency. That is a little bit difficult notion. So, I simply assume that there are 1,000 samples in a second. So in that case, period times 1,000 is equal to 60 over 1,000. This is the wavelength. Okay. The unit is point. So once we have this kind of a sinusoidal signal, there are 1,000 over 60 samples in a waveform, and this means that the normalized angular frequency is because this is representing the 2 pi in the angular domain. Then when you divide 2 pi by this value, means 1,000 times 60. This is the omega 0 for the cosine function. That is 12. 12 pi over 10. That was wrong. Sorry, 10 over 12 pi. That is the omega 0. So what we know about power signal noise is a times cosine 10 over 12 pi n plus 5. Sorry, that's the number here. Okay. If you are not studying about electrical engineering or basic engineering, these things are somehow magic to you. But by calculating this kind of things, we can determine the periodicity of the signal, and that can be directly written in a mathematical form. So what I like to say is that we have, because we have some knowledge on the noise. Therefore, we can estimate the noise. Okay. Oh, I got the wrong number. 60 times. なんか間違ってるかな。間違ってないね。20ってなんだこれ。これ2パイの間違い。2パイだねこれ。2パイだねこれ。そういうことか。すいません。そうだねこれ100。Sorry, this is 100. Okay, so we know that the noise, what this noise is. So what we can do is by subtracting this number from observed noise in order to subtract the noise. So it is doable? That is my question to you. we know that this number, I mean, noise can be represented by this mathematical form. And we also know that once we know the noise, simply subtracting from the observed number will give you a real value. So can we do this? Of course not, because we don't know A and phi. So we still have two parameters to be determined in order to subtract from this, which corresponds to the freedom of this of the location and height of this simple sinusoidal component. This can be here, there, or this can be this height or this height by changing A and. Although the simple periodicity will not be changed, the sinusoidal signal have another two freedom. Therefore, we need to also determine those two freedoms. And what happens if you do not know those two freedoms? That actually is misery for you. You know, this is the most or happiest case you have. The noise is exactly represented by this equation. Then subtracting this value from this will give you a complete zero. Congratulations. But suppose you miss the one sample delay. You know, the location of the sinusoidal component is shifted from the real noise in one sample, only one sample, gives you this another noise. So this doesn't help you much. And suppose that the 8 sample delay gives you more, double error because it, enhances the error component by adding or by subtracting the, antiphase sinusoidal signal. So what I like to say is simply subtracting the signal, noise signal, is pretty difficult. So it doesn't work. That is my point here. So the simple signal subtraction is not easy due to the lack of knowledge about the noise. We also need phase and also the amplitude information. Even we know the periodicity of the power spectrum, power supply noise. And there are commonly used two solutions. One is eliminating any sinusoidal signals which has the lower frequency from the 100 Hertz. The people who do not understand the idea of the lower frequency or high-pass filtering, this is like that. Probably it is not easy for you to understand the signal and the frequency component. But actually, the signal has can be represented by a frequency spectrum, which is another signal indexed by F. This is the frequency measured by Hertz. Usually, any signal has any shape of the frequency, power spectrum shape like this. And suppose that because this noise has only one single frequency component, which is 60 Hertz, it has very strong comparing to the other signals. And this is a 60 Hertz. And very important component of the signal are here, for instance, more than 100 Hertz here. In this case, you can neglect all signal component which has a spectral component left-hand side of this line. So you're gonna disregard this part, which gives you the clear signal, noiseless signal, but lower component will be disappeared. Therefore, the signal will be slightly different from what you like to do or what you like to have. But if you are lucky, the overlapping of the signal component and sinusoidal noise component are apart, like here, then this works very good. So, using the or disregarding the lower component or higher component was what I mostly used when I was a student to get a better experimental result for the lab. So noise sometimes lie on this domain or this area, very, very high frequency or very, very low frequency against to the meaningful frequency region. But that is not general, so you cannot suppose that. But that is one way. And the other way is very general and commonly used, in particular speech for these 40 or 50 years. And I think this is also very useful for various kind of time sequence. But little bit difficult to understand. So if you like to bring this idea, you're going to have a very big benefit in your future research. But if you cannot understand this, I'm sorry, I need to apologize that my explanation is not enough. But anyway, you can search this word, spectral subtraction. You can Google this. Then you can, of course, get a huge amount of text or slides. So please memorize this word, spectral subtraction. This is very general way of signal denoising, particularly for the time sequence. And I highly recommend to use this for the particular applications, like a speech, okay, like an image, okay. So what is spectral subtraction? In order to explain you what is spectral subtraction, I need to explain what is a spectrum. And how many of you do not know or have not studied spectrum? Please raise your hand. You don't? No? So most of you are familiar with that. So unfortunately, I'm afraid that I have enough time to study or to tell what is the spectrum. But so please forgive me, skip that part. But if you need, I think I can spend time for you after the lecture. Well, anyway, spectrum is a frequency, representation. In this case, I didn't use F but K. So signal xn, which is time sequence, can be represented also in a frequency domain, large xk or capital Xk. And if you calculate the absolute value of the capital X, and also if you can somehow estimate the absolute value of the capital D, K, this is the spectrum of the noise, then you can subtract this from this. And if it is positive, then you can use new amplitude of xk by calculating the subtraction this and this and that. Because, if you studied about the Fourier transform, you may know that absolute value of the spectrum is tolerant to the shift of the time. Okay? Do you know? Do you understand? This means that we disregard the phase of the signal. Oh, you're not, okay? Okay, many of you are not so, fluent in the spectrum domain signal processing. Probably I may need, another 1 hour to discuss about that, but I'm sorry. So, okay, anyway, what you have to do now is to, simply write down spectrum subtraction. This may be very useful for you. Sorry, I don't have enough time to go in detail about that. Sorry, but but it is very simple idea, although requires several prerequisites in understanding. Okay, so I don't have time to precisely describe what is spectrum analysis. So, but that is a kind of things. And so I go here, there. Okay. So because I skipped a lot of slides, I have another 30 minutes to discussing about the random noise, and that is the last one third of the present lecture today. So another very common and also annoying noise is random noise. Power signal noise has deterministic characteristics because that has a simple periodic signal. That is a simple periodic signal. But the random noise is random. You cannot foresee, predict, or you cannot determine the value. And some sort of survey result may have a randomness due to the noise, or measurement also. For instance, the thermal noise is a typical random noise, and that is unavoidable for the sort of physical experiments. So random noise is very important to discuss. So what is a random variable? I also guess that some of you have not know fundamental knowledge about random variables. Okay, so the random variables is a variable which represent the uncertain phenomenon or measurement. You can specify the probability distribution, but you cannot know the exact number before you test. Okay? For instance, dice. You cannot know what will be the next try or next throw of the dice. But we all know that the probability that you get 1 is 1/6, right? So these values are very magic value. This is not a deterministic or observable or predetermined things, but we know that the likelihood of the value, and that is very useful, and also give us a lot of knowledge about phenomena. So what is distribution? Distribution is a number 1/6 for each dice number, or head, tail, 0.5, or those values are distribution. Okay, values are distribution. Single probability and the probability distributions of probability distribution are pretty much different. The set of probabilities is a probability distribution that is associated with the numbers of the random variable. Okay, so distribution is how likely the random variable takes the value, and dice is 6/6, and you can specify the expected value. Expected value is a crucially important idea when you talk about data science. We can discuss expected value before observing, but we can know the real value before observing. Okay, so expected value of statistics. For instance, the sum of 3 dices can be calculated by this. Oops. Oh, sorry. So again, and dice is like 1/6. This is for each dice numbers, and expected statistics of sum of 3 dices is it is usually represented by x, and say so this is. Sorry, I think I had a written version of this, but so each one dice, expected value is 6. Do you know 6/22? Okay. Do you know? Does this mean 20/6? This is a number that you have, 1 plus 2 plus 3 plus 4 plus 5 plus 6. Okay, this is 22. Okay, so what we need to calculate the expected value of the dice before you throw. It is like that. If it is 1, the possibility is 61. Suppose that it is 2, the possibility is 62, 6/2. No, 6/1, like that. And you're going to sum up all of them, and what you get is the number 22/6. Okay, this is the expected value. Yeah?
21.
21. Okay, so. Oh, okay. Thank you. Okay, so this is the number 21/6. I'm sorry. Then, again, the expected number of this random variable for the one try is 21/6. Then what will happen when you do that in 3 times and calculating the sum of them? That is also can be calculated by 6 over 21/6, and doing that in 3 times, which is like I don't know, whatever. So it is somehow doable to expect the derivative or combinated phenomenon's expected statistics based on the very fundamental expected statistics. So, for instance, you can calculate the, of course it is not meaningful, but say, for instance, log of the x, x is this random variable. Suppose that x is the random variable's name. Then log of the x and its expected value, doing the same thing, calculating the log and its sum of the samples and doing the same thing. So the point is that even we do not know the exact number of the dice before trying, we can calculate a lot of things because we know the distribution function or probability distribution of the dice number. So that is a very important characteristics, and this is another fundamental principle of the data science. So probability distribution gives you a almost full idea of the phenomenon that you are observing. So when you associate the probability to the signal, we need to extend the idea of the random variable from random variable to the random process. We don't say random variables sequence, but we say random process. So you may have some words, or you may have heard about the random process. That is not a complicated thing, just sequence of the random variable. So the random variable is the random process can be determined by this probability that xn is a certain value, is less than certain value can be given by, say, some function. Say that this is the, for instance, small p, n. So clearly, this is the definition of the probability that the nth sample of the time sequence is lower than or smaller than x0, and the probability is suppose that given by another signal. Then this xn is called the random process. Okay. So here we have two important numbers. One is x0, of course, and the other one is xn. So this sometimes referred as a large f distribution function of xn when the upper bound value x0 is given. So if you change the number of the x0 larger and larger, then the probability will become greater and greater. And finally, that value goes to 1. Okay, x0 and fxn. And the biggest difference from the random variable is that this has another variable m here. And in this case, for instance, if you like to calculate the average of the xn, suppose that we need to calculate the average of xn, xn average, then you need to, or expectation value, yeah, maybe, not average, sorry. I don't know how to say. By the way, do you have the slide which I already written the equations or numbers in it? No? Your slide has also blank here. I'm sorry. I have another slide which has correct equations. Maybe you better to have that. So, but anyway, okay. I like to discuss expectation value, which is usually written like this: x n. So the expectation value for a random process xn is not like the simple random variable. This has also the dependency to the n, like what I call mu n. So if n changes, then the average or expectation value should be also changed. This is a very important characteristics of random process. Okay? But suppose that the random process is the stationary, which means that the random process doesn't depend on the shift of the time. Then, in that case, you can say that Exn is constant mu. It doesn't depend on time indexes. Okay. So the stationarity of the signal is quite important to think about the random process. So sorry, I will upload my slide, which has the more clear methods or equations under here afterward. And in that slide, I also mentioned about the variance of the random process. That is also very important statistics. But in this case, I'm going to skip this slide. Okay, this is one typical signal that you see when you have random noise. Suppose that this dotted line is a real signal that should have a measurement, but because of the randomness of the measurement, we have fluctuations from the real value. And not, unlike the previous case, this displacement is not deterministic. You cannot, how do I say, describe these discrepancies based on the simple mathematical representation, like cosine function. So what you can do is, I think, quite limited. If you are very, very lucky, then the noise has zero mean. Its expected value is zero. Or in other words, centered process, which can be represented by that the expected value of noise is equal to zero. And actually, from my experiences, in 50% of the cases, we are lucky because the random noise has these characteristics. Then, actually, you are very lucky because simply calculate the expectation value of the observed data gives you real data because expectation value of additive noise goes to zero. Okay? So how do you calculate this? That is the single question. So am I making sense? Am I making sense to you? So probably you're going to be confused by this notation E. Okay? So you can simply think that E is expectation. Therefore, if the single variable is written here, then you can think about the average value of this random variable when you try multiple times. Okay? So if you can try multiple times and can calculate the average value of those trials, then the result will be real value. Multiple trials. Because the randomness of the noise is completely random here and there. So these discrepancy or differences going to be end up with zero when you add these discrepancies. Okay, so the idea is very simple, but it doesn't work with the twice or three times, very few times of trials, because it's not always very balanced. It depends on the cases that you are facing. So usually we do 5 times, 10 times overlapping add. That gives you the real value. So suppose that we have same signal observing, measuring, but different noisy signal in each time. So you're going to try once, twice, 3 times, 4 times, 10 times, and calculate the average. Of course, you need to adjust the time horizon so that the target signal is coherent with each other. But then, in this time, the positive error, negative error, big positive, big negative, blah, 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 blah. We're going to give you finally 0 mean, and that gives you a very accurate estimate of the unchanged component, and that is the real signal. Okay, so this is one idea you can remember, and you can do this very easily and very widely. And also, if the signal can be regarded as a sinusoidal or periodic signal, then you can do something very similar with one observation. You cut this single part, and you cut another, one period, and you cut another one period. And if these if this real signal does not change over the trials or over the time sequences, then you do exactly have the same thing here, but the error noise are different. So by calculating the sum of them, and you're going to have a good estimate of SN. This is another version, which we called synchronized add technique, or overlapping add technique. So if you remember this kind of things, you're going to have a very easy way to suppress the noise. Okay, and this is my case. Okay, another, but same idea is, this is the actually final idea of denoising that I talked today, is to use the difference in the speed of changing of the signal. If you measure the signal in a very high frequency, sampling frequency, which means that because this is very slowly changing signal, that is what you like to measure. But even if, though you can use a very high frequency sampling like this, a lot of samples should be sampled here and there, then what you're going to have is something like this, here, there, because of the error. But you have a lot of observation for the small portion of the signal. Therefore, you can also average this, and this. Then what you will have is somehow a good estimate of the real signal because of the also the zero mean characteristics of the error, right? So this is another simple technique, and this sometimes called the average filter as a denoising system, which cancels the random component. Again, this is another another implementation of this actually is low pass filtering, but I don't mention about that. But I know much more better way, much better way to do this. That is the median filter So you also remember the name median filter. I very much recommend you to remember this name and use this for your time sequence signal or time sequence data. That is very efficient to exclude the, how do I say, extraordinary erroneous data. Because local averaging sometimes very naive to the very big discrepancy of the data like this, because this changes the average value very much. But if you use a median, central value, central value, median, you can easily disregard this such extremes in a data distribution. Therefore, you're going to have a much more steady estimate of the data. So we usually use the median filter a lot, whatever we measure. If we can suppose that the real signal doesn't change very fast or rapidly. So please remember the word median filter. So this is very useful from my experience. Okay, so I think I used almost my time. Really? No? I did. 大丈夫1時間半でしたっけ Okay. So here's a real result which you apply. When you apply the median filter for this shaggy noise signal, the result is like this and like this. So it looks much more similar to the real data. And if you calculate the average, if you use the average filter, it may look better, but because of the smoothness, too much smoothness of the averaging result, you're going to have a peak here or there. So these things are not good, actually, for applying. I say worse than the median filter. And comb filter is another name of the overlapping ad. This is another word called comb filter. I cannot, explain why do they call comb, but it is really reasonable, again, actually. But if you apply this, you I think better result than using the average filter. So this looks very nice and very similar to the real data. So I guess you're gonna experience the comb filter in a exercise lab. Will they? What will you do for the exercise or practice, Suzuki Sensei? I believe you're gonna teach about. They're gonna experience the comb filter for the lab. Okay, so you're gonna experience the comb filter, and if you can learn how to use that, you're gonna have a big merit for your data analysis project. Here's a result summary, but it is not so important. So, okay, so I finally reached to my final slide. So, in summary, in this lecture, I have explained that the signal is the data, but it is a sequence. It is a sequence of time or space, and also additive noise is the simplest cases of the mathematical representation. And from my experience, additive noise is the most important, and what we should do first. And signal to noise ratio, this is not mentioned in our lecture. And frequency filtering, that is one idea to utilize. Particularly important idea is spectral subtraction. And in another idea, which is very efficient for the random noise, is the local averaging. And local averaging can be characterized by two different ways of averaging. One is simple averaging, and the other one is median ablation. And median ablation is more robust to the extreme of the error. So, a lot of state-of-the-art method. For instance, in speech area, we have, modern, hundreds of new methods for denoising are proposed in a year by a lot of researchers. And some of them are very, very novel and very efficient for the particular class of signals. But that is not efficient for the particular class of another class of signals. So what I have told you today is very general method. Therefore, I think all of those things, method can be applicable to your own future research project. So please remember these methods by names only, and you can later study using the Google or another text. That would be what you need to do in the future. Okay, thank you very much, and see you next week.